Good morning, everybody.
Good morning.
Okay. As a reminder, we're going to have our second midterm on Wednesday, and we talked about the topics that we're going to cover on the exam. Any questions? Questions on the materials? You guys doing the homeworks every week? Catching up? Everybody's up to speed?
Yeah, in a second.
I mean, if not, at least you will be by Wednesday, hopefully. And then you look at the homework like, whoa, when did they assigned? Never seen this before. Okay. So in the previous classes, we talked about the root locus and what was the idea behind doing the root locus.
Finding the range of where the zeros could be.
What else? The zeros, zeros of the characteristic equations, which is the poles of the closed loop system. But what's the idea behind, why were we doing this?
See how they changes the gain changes.
Because we want to see how the response of the system changes as we change one of the parameters, which is usually the gain. And how is that? Because we know when we looked at the second order system, if the poles are in this region, then the system is going to be underdamped. If the poles are on this axis, then the system is going to be overdamped. And the more the poles go up, the more the system underdamped. The more they go down, the more it is overdamped. So if I have a root locus, for instance, that looks like this, and I can control how the system is going to behave by controlling the gain that will place the poles at any of these locations. Make sense, everybody? But then we said, what happens if I have a root locus and we plotted it and we thought using the gain alone is going to enable us to control the system and give us the behavior we want. But then after we plotted the root locus, we realized changing the gain alone is not enough. I want my system to have poles at this location, at these two locations. And if I change the gain alone from the root locus, there is no way I'm going to be operating at this point. So in order for me to be able to operate at these points, we said we have to change the dynamic of the system. We have to add poles and zero such that the new root locus is going to pass through these poles and I will be operating at these points. Is that clear, everybody? And this is what we said to do in this part of the course, which is the controller design. So therefore, we said in this part, we're going to have a controller that we will be designing we have the gain, we have our system, G of S, our plant. And we're going to be designing a controller that is going to be adding zeros and poles to the system in such a way to meet a certain design requirements. Now, if I like to change the performance of the system, then most likely I'm going to be interested in one of two things. Either I want to improve the transient response of the system, or I want to improve the steady state error of the system. So I either want the transient response to improve, reduce an overshoot, or improve the rise time, etc., or I want in the steady state to have less error. So therefore, we're going to look at two categories of the performance, which is improving the steady state error and then we're going to look at improving the transient response. And then we're going to combine all that. We're going to look at the controller that will do both. Okay. So then we said if we want to design a controller that will improve the steady state error, we have two choices. We can have an active device, which we said it's a device that will require a power supply like an op-amp, or we can have a passive circuit. a circuit that does not require a supply to operate. And if we are using an active device, we'll be able to design what we call a PI controller, which is a proportional and integral. And if we are using a passive circuit, we're going to be designing a controller that we call a lag compensator. And this compensator is going to have a transfer function that is S plus ZC divided by S plus PC. And the PI controller is going to have a transfer function that is S plus A divided by S. Does that make sense, everybody? I mean, the reason I list all these because I want you to be able to see what we are doing as we go through, because we're going to go through each one of these. But if we are in the middle of discussing any one of them, I want you to be able to see the full picture of what we're trying to do. So then we said also we can improve the transient response. And the same thing, we can have a passive circuit, or we can have an active circuit. And if you have a passive circuit, we're going to call it a lead compensator. And it's going to have a transfer function that is S plus ZC divided by S plus PC. And if we have an active compensator, we're going to have a proportional plus derivative. And we call this a PD compensator. And it's going to have a transfer function that is S plus ZC. Okay. Now, if I look at this lag compensator and lead compensator, they look like they're the same, aren't they? What is the difference between them? Is where I choose the location of the pole and the location of the zero. If I choose ZC over PC to be much, much larger than 1, then it will be a lag compensator. If I choose ZC over PC to be less than 1, it's going to be a lead compensator. And then we're going to look at the PID compensator, which is going to be the PI plus the PD. Okay. Now, before we start looking at the compensators, if I look at the lag compensator, so I am at this part here. We said we're going to have ZC that is much larger than PC. So therefore, we're going to have a system that might look, a compensator that might look something like this. ZC is larger than PC. And therefore, if I come here and take any point in the S space and look at the contribution of the angles, phi 2, and this is phi 1. And remember, what is the angular criteria for the root locus?
G of S1 and H of S1 is 180 degrees.
Yes, and one way to say that is the summation of the angles from the zeros minus the summation of the angles from the poles must equal an odd multiple of 180 degrees. Gonna remember that?
I'm gonna write it down.
I'm sure we wrote it down. Okay. So therefore, if I am at this location, and if this location used to be on the root locus, now I'm adding pole and a 0. Is this location going to be on the root locus still? Okay, the question in slow motion. This location, this point here, used to be on the root locus. Then I came to the system and I added this 0 and this pole. Will this location still be, I'm sorry, for people in Fort Walton, I'm talking about this point here. This point is on the root locus. It used to be on the root locus. Now I added this pole and this 0. Will this location still be on the root locus?
No.
It will not, because I added an angle phi 2 minus phi 1. That is, if the summation of the angles from poles and zeros was 180, and now I'm adding something that is not 0, it's not going to be on the root locus. Together? Is that clear? Okay. So if I look at phi 2 minus phi 1, is this going to be greater than 0 or less than 0? Less than 0. This, might be 45 degrees. This is 110. Therefore, it's going to add an angle that is less than 0. If I look at the second case, and in this case, I have the 0, 0 over the pole, much smaller than 0. So therefore, I have the 0 to the right and the pole to the left. And if I take the angle phi 1, take phi 2, then phi 1 minus phi 2 is going to be greater than 0. Is that clear, everybody? Now the question is, what's going to happen to the root locus if I added this compensator, the lag compensator? If I added this pole and 0, what's going to happen to the root locus?
It's going to change.
Excellent.
Good job.
Everything changes. That's why we're here. The root locus is going to move to the right. That's what you meant to say, isn't it? Or did you change your mind? The root locus will move to the left. Together? Why is it going to move to the right?
The location of the pole.
No, not very intuitive. So I don't expect anybody to give me a very good answer.
I imagine it kind of pushes it.
What is it?
I said, I imagine the pole pushes it.
Okay, so let's see if I have a system. I'm going to take an example of a system that has a root locus that looks like this. Does anybody know what system will have a root locus that looks like this? What is the system that will produce this root locus? You don't need to look anywhere other than this graph.
Are you looking for like critically, like?
No, it's really, it's straightforward.
Like the order of the system?
Which one?
Are you looking at the order of the system?
No, what the transfer function gonna look like? When we've done it before, we've done this before. But I don't expect you to remember that we've done it before, of course. But I expect you to be able to look at this and say, oh, okay, yeah, this is.
This is what.
What did this?
And what is what I'm looking for?
What
Anybody?
is it like whatever S?
There's one here, there's one there.
There's like,
They
and
come
then the
together and
integrator or
they
something.
split up.
No, I mean, it's not guessing. Although I appreciate the effort in guessing. I have a pole here, isn't it? So therefore,
Number S times S plus.
excellent. And remind me, your name?
Correct.
Oh,
Greg?
Craig.
It's a star.
Craig.
Star. Yeah.
Excellent.
Yeah.
Isn't that the second star you did?
No.
Second,
Today's first.
Yeah, he got it in the lab.
if you get a 10 stars, oh, I should not make promises I cannot keep. Okay, so this looks like 1 over S multiplied by S plus whatever this pole is. 2 poles, in the middle, they're going to split. Make sense? And again, when you study the root locus, please keep this in mind. You're going to see it. We've done something like this. Okay, so if I take any point on this root locus, so if this used to be, for instance, negative 4, this is 0, where is this going to be? Right in the middle. So this is going to be at 2, at negative 2. This line, that is vertical. Make sense? And if I take any point here, how do I know it's on the root locus? I'm going to do the angle criteria. And if I look at the angle criteria here, I'm going to take this angle, this angle. What is this angle going to equal to?
135.
I mean, it depends on where I am, but yes, if I take it to be at this point, it's 2. This is going to be 135. And what is this going to be? 45. Make sense? 135. And if I add to it the 45, it's going to be 180 degrees. Make sense? Or negative 180 degrees. And therefore, it is on the root locus. Make sense? I mean, this is what we know. Now, what happens if I added a pole and a 0 like this configuration? So I came here to this, and I'm going to just zoom in. I came here, and I added this pole and this 0 to this system. So I added a pole here, and I added a 0. We said this pole and 0 that I added is going to contribute an angle that is less than 0. So let's say it contributes an angle that is negative 20 degrees. Make sense? What's going to happen? What is these angles have to? What is going to happen to this point in order for it to be still on the root locus? It's going to have to move to the right. Why? Because if I move to the right, then this angle from the original pole is going to get smaller, isn't it? It's going to become, let's say, 120. This angle too is going to get smaller. Let's say this becomes now a 30. A 30 and 120 is 150, but then I also have a 30 that is contributed from here. Is going to make it 180 degrees again. Is that clear? Makes sense? Now let's make it other than 30 so it's not confusing. Let's make this 40 plus a 40 plus a 20, and the 20 is coming from here. Okay. So therefore, if we design a lag compensator And of course, you can easily verify this with MATLAB with the root locus command. You can create the root locus with added poles and zeros. Let me write it down, and you can verify it if you like. So you can plot the root locus. Okay, so the root locus is going to move to the right with the lag compensator, is going to move to the left with the lead compensator. Is this good or bad to move to the right?
Bad.
Bad. Why?
I guess it's lag.
Why is it good? Why is it bad?
We're moving towards instability.
Exactly, because we're moving towards instability. So if I was originally operating, for instance, at a point that I'm very close to the j omega axis, and then I'm going to design a lag compensator, I'm going to find myself moving to the right half plane and becoming unstable. Make sense, everybody? Okay. Of course, this is negative. I should have. This is negative minus 40 minus the 20. Okay, so let's look at our first compensator that we're going to look at. So we're going to be looking at the PI compensator. It's an active circuit, proportional plus integrator. Now, can you see what the similarity between these two together? What is the similarity between this and this? Why do we have them in one category?
Are they both going to move the root locus the same?
Yeah. Why?
Um,
What is the similarity between these two that we have them together?
Does integral relate to like integration? That's
Well, yeah.
whatever s.
Yeah,
Does that have to do with anything?
it does.
Okay.
But what else? Like, what's the similarity between this one and this one?
Oh.
Oh, and people at Fort Walton. What is the similarity between this transfer function and this transfer function?
Time zero.
For both of them, the pole is closer to the j omega axis than the zero. Here, it so happened to be at 0. Does that make sense? So here, I have a pole and a 0. Here, I have a pole and a 0. If I make PC equal to a 0, move this to the right, then I will be the PI compensator. Does that make sense? Why like they're the same? Both of them are going to contribute an angle that is negative. Maybe I should. So for this, I'm going to have a pole here. I'm going to have a 0 here. So you can see the similarity between them. This, the pole is not at 0, to the left of the 0. There it is at 0. Okay. So let's start with our first compensator, which is the PI controller, which is going to improve the steady state error. And we know in order to improve the steady state error, what do we have to do? What do we do to improve the steady state error? We?
I said reduce the time, because that's something
Yes, we can increase the type. We can increase the type. How do we increase the type of the system? We add add an integrator. Excellent. We add a pole at the origin. I mean, remember this from the table that we generated. Well, hopefully you remember that before Wednesday, when we calculated the steady state error. The higher the system type, the less the steady state error is. However, what we want is we want to improve the steady state error without affecting the response of the system. What does that mean? I want the response of the system not to change when I improve the steady state error. So let's look at 3 cases. So in the first case, we have the system, and we plot the root locus for this system. And the root locus looks something, let's say, like this. We have pole there. And we are operating at this point here. We're going to call it A. And we are very happy with the performance of the system, except for the steady state error. We need to improve it. So what do? We add an integrator. What happens when we add an integrator? We're going to be adding another pole. Now all of a sudden, my root locus is going to look something like this. What happened here? This point that we used to operate at, that we like the performance at, is no longer on the root locus. Does that make sense? Like why I can just add an integrator to the system and expect it to improve the steady state error, because it's also going to affect the transient response, because the point that I used to operate at, that used to be on the root locus, when I add an integrator, it will no longer be on the root locus. Make sense? So what do I have to do? I'm going to add a 0, and I'm going to add a pole to my system. And now, what is it we're going to have? we have the pole that we added, and we have a 0 that is very close to it, and we have the original poles of the system. And hopefully we are still be able to operate at the point A. Does anybody know why? Yes, what else? Why is it at this point A is on the root locus, and in this point A is also on the root locus? I mean, not exactly A, but A is very close to the root locus compared to here.
Could you move the root locus back?
Because if I look at the angle criteria, this used to operate. This used to be part of the root locus when I was operating here. Now I had a pole and a 0, but the contribution of the pole and the 0 are so close to each other they're going to cancel out. Does that make sense? So if the angles used to be 180, most likely they're going to be very close to 180 still. Is that clear, everybody? So what I'm saying, if I take the contribution of this angle, the contribution of this angle minus this angle, what is that contribution? It's very small. So therefore, either I'm going to be operating at A or, well, I'm not going to be operating for sure at A because I am contributing an angle, but I'm going to be operating very close to where A used to operate. Okay. So therefore, we can say A in this case belongs to the root locus. A does not belong to the root locus. A belongs again to the root locus. And to be more accurate, we're going to mark A as like a bigger region. Okay, so how does this PI controller look like? So if I look at the circuit of the PI controller, we said this uses an active circuit, and it looks something like this. This is Z1, this is Z2, and the output over the input is equal to negative Z2 over Z1, which is going to equal to negative R2 plus 1 over SC divided by R1, which we can write as negative R2 over R1 multiplied by S plus 1 over R2 divided by S. What is this transfer function going to give me? It's going to give me a pole at the origin, and it's going to give me a 0 that we can choose to be very close to the origin. So here is a 0, and here is a pole. Okay, is that clear, everybody? Any questions? Okay. Let's do an example. Okay, so we have a system I'm gonna sneeze. I'm gonna design a compensator to improve the steady state error. Okay. And the system that we're talking about looks something like this. What is the first thing we're gonna do?
Draw the axis.
Draw the
And then plot.
we're gonna plot the root locus, no? Root locus or just the axis?
The axis of the locus.
Okay, we're gonna plot the root locus. Where are the poles of this system?
-1, -2.
-2, and far away here, -10. How many asymptotes does the system have? 3. Which part on the real axis is on the root locus?
10.
And what are the angles of the asymptotes? 60, -60, and 180. The root locus looks something like this. Together? Okay, so we have the system that is operating at zeta equal to 0.174. Where is it, at what point on the root locus am I operating? How do I find that out?
The angle right here. Like this, J omega, Z omega. I'm not sure.
How do I know where I'm operating on the root locus? Oh, come on. I mean, I know you guys prepared for the exam. Don't try to act like this so I make the exam harder. How do I know using the information that we have on the board, at what point on the root locus I'm operating.
Seems like a good question for Fort Walton.
Oh, thanks for volunteering that.
Is there a K?
We lost contact with Fort Walton, so we have to solve
Is there a K value?
Do we use the damping ratio?
the,
Do we use the damping ratio? Given
the which equation?
the damping ratio?
Yeah. What else?
Do we use zeta equals 1 over? Oh, never mind.
Did anybody prepare their formula sheet for the exam? Maybe that's
Capstone is
Yeah.
very hard.
Like 9 a.m. to 1:30 in the morning, it's capstone.
capstone on Thursday.
It's been
Every day.
It's been every day.
It's been
Constant.
constant.
We have VIEs this week.
Yeah.
I want to tell you something, but we are recording, so I cannot say it. Remind me after the exam,
You had 9
after the
months.
class.
Okay.
Okay, so how do we find, given that zeta is, I mean, if you look at this root locus, what is zeta if I'm operating here?
Very small.
Zeta is greater than 1. Eventually, zeta is going to equal to 1. Zeta is going to become less than 1. It's smaller and smaller as we go farther. How do I know where I'm operating if zeta is equal to this value? We've done it in the previous class. We said zeta equal to 0.174. Therefore, theta that this pole makes is equal to cosine inverse of 0.174, which is going to equal to 79.98 degrees. And therefore, I can come to the root locus here, plot a line that makes 79 degrees. What does this line represent? All the pole locations that will have zeta equal to 0.174. Now, if I take the intersection between these two curves, I'm going to be operating at this point here. And this point corresponds to K that is equal to 164. Is that clear?
How'd you get K equal to 164?
That's where he does like this right here, the two
Oh.
zeta W and
Okay, yeah. So it's
omega n equal, right? I thought, right?
Well, we'll see how we're going
My
to get
brain's
down
doing
64 in a
that
minute.
right now.
But for the time being, everybody agrees to this? Everybody feels like, oh, I should have answered this? Or I probably didn't, I don't want to answer because I don't want people to think I know it.
That's bothering me.
I don't want people to think I'm the only one who knows. Straightforward. Zeta, intersection of the curves, will give us the point where we are operating at. This corresponds to zeta equal to 1.74. Can anybody tell me, when we measured the angles for the root locus, we used to measure the angles like this. Why am I measuring the angle like this?
Oh,
What is it?
they can't see, that's what she was saying.
No, I
They can't
thought-
see where you're pointing.
I have the step mat on. Oh, that region. The whole board you cannot see?
Oh, it's behind them. Like, see the screen behind them? Behind them? See, like, right there, so they can see.
Oh, okay, because it's very small. Is it because it's very small? Okay. Okay, so we'll try to stay here. Okay, so the question that we were asking.
Why is it 79?
Like we measured the angle here, 79, from the negative axis. But with the root locus, we used to measure the angle from this way. Anybody knows why? Okay, you don't need to know why, but anybody not confused? Anybody confused? You confused?
Why is it 79? We don't need to know.
Which one? Now I'm confused.
I don't know why it's 79 versus.
79, we measured it from here because the way we defined it, we derived it, it was according to theta was defined with the negative axis. Okay, so I just don't want somebody to say, oh, a minute ago we were measuring the angle here, now I'm confused. One time he's measuring the angle this way, one time he's measuring from. This is when we derived the zeta, we derived it, we defined theta with the negative real axis. So if you're studying, you should not be confused. But I was tricking you to see who studied. Okay. So we found this point. We found the poles, S1 and 2. They're going to be negative 0.69 plus or minus J 3.9. And K is equal to 164. Make sense? So the point, that point that we marked there, this point, corresponds to negative 0.69 plus or minus J 3.9. Okay. So now if we designed a compensator, we can calculate the steady state error Kp is going to equal to 164 divided by 1 times 2 times 10, which is equal to 8.2. So this is the steady state error without the compensator. The original steady state error. And therefore the steady state error is going to equal to 1 over 1 plus Kp, which is going to equal to 1 over 1 plus 8.2, which is going to equal to 0.108. What is the steady state error with the compensator? We have K that is equal to 164 divided by S plus 1, S plus 2, S plus 10. We have S plus 0.1 divided by S. Okay. So we calculated the steady state error. It was 0.1. We're going to improve that steady state error. So what is it we've done? We said we have to increase the system time. We had to do a PI controller. We added a pole at S. But I also have to add a 0. I chose the 0 to be at 0.1. Where did this come from? I'm going to choose the 0 as close to the pole as possible. Does that make sense? So I could have chosen S plus 0.05, S plus 0.2, whatever I mean, again, this is an active circuit. It's an op-amp RC circuit. Whatever components you can find that will place the pole as the zero as close to the pole as possible. Make sense, everybody? Okay. So therefore, what is the steady state error that is going to happen with the compensator? If are talking about a step, what is the steady state error going to equal to now? Now the system is type 1. The steady state error is going to equal to a 0. Make sense? Are we done? No. We're going to have to go back to the root locus and plot the root locus and see if I'm still operating at that point. So I'm going to come to the root locus here, and now we have a pole at the origin. We have a 0 very close to it. We have a pole at -1. We have a pole at -2. We have a pole at -10. And now I have a root locus that looks something like this. Does it look like the one before? Almost. But apparently, I mean, it should not be exactly the same like the one before, because we added a pole and a 0, and even though their impact is small, it's still going to move the root locus. So what I'm going to do, I'm going to still plot the line that represents zeta that was equal to 0.174, and I'm going to find that the intersection point now happens when k is equal to 158. So therefore, I'm going to come back here. Sorry, this should not have been 64, 158. Is that clear, everybody?
How are you solving for K?
That's what we're going to do next. But for the time being, I went to MATLAB and I kept moving around the root locus till I found zeta equal this value, k was equal to 158. Is that clear, everybody, what we've done? So again, looking at both of these with the without the compensator, I was working with zeta equal to 164. I had a damping ratio zeta that was equal to 0.174. Now I added this pole and 0. Therefore, the root locus moved to the right a little bit, such that I had to have, again, that is equal 158 to be operating at that zeta. But what did I gain out of this? I have a steady state error that is equal to a 0. Is that clear, everybody? Okay. The next question is, how do I find the point that I'm operating at? How do I find this point here? On the exam. Any ideas? Solve for using Yes, but I found the pole because I know the value of k. Any ideas how we can find this point?
Zeta has to be the same. You just find the intersection. Zeta related to K. Solve for K.
So we know zeta, so we can get an angle out of that. Then can we use like the angle formula and put everything in like where it's like the 2k plus 1, like 180 degrees over like the number of poles, number of zeros, and then just find k that way.
Like this space, I would say.
Probably not. That's not the right way.
Okay. Anybody want to give it a shot?
Did you find the natural frequency?
What is it?
Did you find the natural frequency of the system?
What else? Fort Walton? Okay. Okay, so let's see how, if we ever see this on the exam, we're going to be able to solve. Okay, so we're going to solve this for this value of zeta, but apparently you can solve it for any zeta. So the system that we've seen okay. So if I'm going to solve this graphically, what do we have to do? We took the point 174, we found the theta that corresponds to that, which was 79. We plotted a line, we looked at the intersection, and we said this is the point I'm operating at. And this angle was 79. So this is the point I'm trying to find. Now if I'm going to call this point S0. And this S0 is going to have a real part and imaginary part. I'm going to call the imaginary part B. I'm going to call the real part A. So how many unknowns we need to solve for? We need to solve for A, we need to solve for B, and we need to solve for K that gives me this intersection. Make sense? Remember, as I vary K, I'm moving around the root locus. There is a value K that I'm going to be operating at this point. K changes. I'm moving at certain value of K. I'm going to be at this point. I want to know this value of K. Okay, so what are the unknowns? K is unknown, B is unknown, and A is unknown. So I have 3 unknowns. How many equations I need to solve for 3 unknowns? 3 equations. What is the first equation that I can see on the board here that will help me reduce the unknowns to 2 unknowns? B and A are related by this tan, isn't it? S0 is equal to negative A plus J multiplied by B. But the tangent of 79 degrees is equal to B divided by A, which is equal to 5.6. So therefore, S0 is equal to negative A plus J 5.6 multiplied by A. Together? How many unknowns we have now? 2 unknowns. Only A and K. Okay. What other information we have about S0? What else we know about S0? S0 is part of the root locus. If it's part of the root locus, what does that mean? It satisfies the characteristic equation. S0 belongs to the root locus. So therefore, if I take S plus 1 multiplied by S plus 2 multiplied by S plus 10 plus K must equal to S0. Is that clear? This is S0 is a pole of the closed loop system. What does that mean? It means if I calculate the closed loop transfer function, this is going to be a pole. Okay. So therefore, I can write this as S cubed plus 13S squared plus 32S plus 20 plus K equal to 0. Now if I substitute for S with S0, it should satisfy this equation. So therefore, I'm going to come to S0 and say negative A plus J 5.6 cube multiplied by A together. How many equations does this equation give me? How many equations does this equation have? How many unknowns does this equation have? 2 unknowns, K and A. And how many equations does it give me? 2. How does it give me 2 equations? It has real part and imaginary part, isn't it? The real part must equal to a 0 and the imaginary part must equal to a 0. See it? It has imaginary part. If this is equal to 0, the real part must equal to a 0 and the imaginary part must equal to a 0. Together? Okay, so therefore, we're going to take the real part and say we're going to need the real part to equal to a 0. We're going to take, so this is 2 unknowns. We're going to take real part We're going to equate it to a 0. We're going to take imaginary part. We're going to equate it to a 0. Make sense? So with some simple math manipulations, and assuming I did not make any typos, but please verify this when you go home after the exam. And it's 32a plus k plus 20 equal to a 0. And we're going to have another equation that is coming from the imaginary part, 19852a cubed over 125 plus 728a squared divided by 5 minus 89.68 divided by 5 equal to a 0. What do we do next? We're going to solve this equation. It's going to give me how many values of a? It's going to give me 3 values. A equal to a 0, a equal to negative 1.6, and it's going to give me a equal to 0.698. So all of these values will satisfy this equation. What am I going to do with the first one? I'm going to drop it. What am I going to do with the second one? I'm going to drop it. What am I going to do with the third one? I'm going to take it. Why did we drop the first one? It's a trivial case, 0. Why did we drop the second one? Negative, which is going to make the pole on the right side, because we defined it as negative a. Or, sorry, we defined it as negative a. A 0 is negative a. So if it was negative, negative of the negative is going to be equal to, is going to be on the right side. Does that make sense, everybody? So the pole is negative a plus jb. And therefore, the value that will interest us is the 0.698. And then I can come to this equation, plug in the value of a, and that will give me the value of k, which is equal to 164. And therefore, S0 is going to equal to negative 0.698 plus or minus j 5.6, and k is equal to 164. Is that clear, everybody? And therefore, if we are given any root locus and I want to find the intersection of that root locus with any given specifications, we can always do something like this. If we are given zeta, we can relate the real and imaginary, then plug that point in the root locus, solve for the real part, and then get the imaginary part, and solve for k. Make sense? Everybody? Look. Now apparently this is lots of math. So we have two choices. Either allow you to use MATLAB on the final exam, which is not going to happen. What is the last choice we left with?
No final.
Oh, that's a trivial answer. That's not. That's like the 0.
You don't have a question like this today.
Uh,
Just trust that we know what we're doing.
That's the second answer that is rejected.
Take home final.
If we have something, it's going to be something that you really can solve. Does that make sense? I mean, there is a way to make it simpler that you can just solve it easily. Makes sense? We're going to have something on the final where a curve is going to intersect a curve. But it will be such that you can solve it with much simpler math, but the same concept. Okay. So now that we covered the first compensator, so we covered the active PI compensator, add a pole, add a zero very close to the pole so that it cancels its impact on the transient response, but it will increase the system pi by 1. We're going to look at the second compensator, which is the lag compensator. So the second compensator is the lag compensator. And this circuit is a passive circuit. And the circuit looks something like this. What is the relationship between output and input? Okay, so V output over V input, as you know, this is a voltage divider. This impedance over the total impedance, we can write it in this form. And therefore, we can write it as equal again multiplied by S plus ZC divided by S plus PC. And therefore, this circuit, we can choose the components so that we have a pole very close to the origin and a zero to the left of that pole. Is it possible to have this PC at the origin? Why?
Because the pole would be 0. And then S, and the whole thing would be like infinity or something.
We can't, because in order for this pole to be at the origin, we're going to have PC equal to a 0. Isn't it? For PC to equal to a 0, we're going to need R1 to be infinity, or R2 infinity, or C equal to a 0, which will open the circuit. Makes sense? So all of these are finite, and therefore we're going to have finite pole. But we can tell, looking at this circuit, by similarity to the first circuit we looked at, which is when we had the pole here and the 0 here, we improved the steady state error. So we're going to expect the same thing. This is also going to improve the steady state error. Okay. So how does this circuit how does the lag compensator improve the steady state error? And that's what we will find out a week from today.